Um, on your calculator, get into parametric mode. So highlight the PAR, and it'll go to parametric mode. Go ahead and go to your y equals menu and enter those in. You'll see, maybe I'll do this too. You'll see when you get there, clear this out. So it would look like this, mode, and then function, parametric. Oh, I said it backwards. It's parametric first. So convert over to parametric mode, and go ahead and push your y equals button, and this is where things look pretty different, right? And normally when you push your y equals button, you just get y1 equals, y2 equals, et cetera, et cetera. And so this time it's x1 with a little t and y1 with a little t. And so let's see here, this first example, let me do it like this. There we go. So we're going to enter x1 equals 5 cosine t. And notice this time, for the first time ever, when you push that little xt theta n button, a t shows up because you're in parametric mode. And then for y1, we're going to just push 0. And then something a little bit unique here. It says highlight the slash on the left and press enter twice. I can't remember if twice is the right number of times. We'll push it the right number of times. So let's see here. I want, oh yeah, this is a little bit different. So did you guys have this show up? Did you get a little dialog box?
No.
Okay, so if you didn't get a little dialog box, I'll show you what you want to get. You want maybe the little ball with a line next to it. Do you see that? So it looks like a key, sure. So you might have to, if you don't have this newer operating system, you might have to hit the little slash a couple of times to get to that, but I'd like to get to this right here. This will allow us to kind of see what's happening with the parametric. You hit OK, or you just get off of that screen, whatever it might be. There we go. Okay, and then finally your window. It wants you to set your window from 0 to 30. So push window. So tmin is 0 right now. I want my tmax to be 30. We'll leave the rest of it alone. We'll talk about the t step, and I think normal window plus or minus 10 on everything will be fine. So once you have all that set, then you just hit graph, and when you do, be ready to watch the little ball moving around, because it should move around hopefully like this. Is yours going back and forth like mine? Yours is doing what?
I just don't see anything.
So you need to get to the where you've got the ball that shows up. Yeah, so go arrow left. There you go. Now hit enter. Whoops. Enter. There. Oh, too many times. Go back to the ball with the line. There you go. Now hit graph.
Yeah.
And now you should see it.
Thank you.
So go back to your y equals. Looks like that's also good. Let's turn those off. So like go scroll up. Hit enter. And go over right. Enter. Let's see if that makes any difference. Oh, you know what? Let's change your window. So negative 10 to 10, and then on your y min and max, go negative 10 to 10.
I'm going to try again. I'll just put regraph it. Or not.
There it is.
Ask it.
Oh, it's going super slow. Let's go 21. No. There you go. Yep.
Oh, there
Mine's
it
still
is.
not working.
Oh, come on, Lynn. What did you do to your calculator?
I don't know.
You probably have a really tiny t-step.
Well, mine's 0.13 and hers is 0.1.
Wow, this is cool.
We can put 2D.
And then I have to admit, I don't know what's going on. Maybe it's this 1 plus 2 thing.
They have a second cap.
Right there.
Second cup.
That's got, we need to use those batteries. Put it in temperature in.
Oh, you're in agreement.
Oh, degree.
Okay.
No,
It gotta be-
doing it while trying to rememorize.
I was trying to do some
the
business
first
last
six.
night.
Okay. So, I am going to, let's see here. Let me do this again and let me talk about what's going on while it's going. So hit graph. So this is basically the proverbial particle moving along the x-axis, right? Haven't we done a million of these problems? A particle moves along the x-axis with velocity such that blah, 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 or its position is this, or its acceleration is that. Isn't that what this is? I mean, literally, it looks like a particle, doesn't it? It's a little ball moving back and forth along the x-axis. So we've done a bunch of these in the past, but now we're going to do something a little more exciting. We are going to free this object to not only move left and right, but up and down at the same time. So it's going to be free to go all over the place. And later on, if you take Calc 3, it'll not only be free to do this, but it'll be free to do this too, like go back and forth and towards you and away from you and go whatever. It's called a vector valued function. That's for stuff for another day. But what I thought we would do is go back to this earlier example we just did. And this time, instead of having y1 be 0, that's why it was just along the x-axis, right? Because the y-coordinate was 0 no matter at what point we were at. This time I want y1 to be ln of t. So I'm going to go y equals, and I'm going to go back in, and instead of 0, I'm going to put natural log of t. And then once again, I'll hit graph. And now it moves very, very differently. You still see it moving left and right, don't you?
Oh my god.
But now as time goes on, it actually is going to move up a little bit as well. So it's going to go left and right, and up at the same time. It doesn't look like this one is actually going to go back down. They could. Just based on the nature of ln of t, it's going to do whatever ln of t tells it to do. So this is a perfect example of a parametric function. Think about what I just said there. Parametric function. I think I mentioned this a little bit later on. When we talk about parametric functions, we are not talking necessarily about y being a function of x, but y and x are both functions of t. All right, so many of these graphs will not pass that vertical line test you guys learned about way back when. Let's see here. So some thoughts I put in here. Mess around with the t-step and see how it affects the graph. So we can do that. Let's see here. In fact, I'm going to change my window like it says here. I'll go window, what was it, -8 to 8. And then the y min would go -3, y max would be 3. But let's mess with the t-step here. T-step is like the number of breadcrumbs that you put down every second. So think about it like this. If I'm going to see this graph and I'm going to be dropping breadcrumbs, if I'm going to drop one breadcrumb every second, I could probably walk this fast, right? But if I'm going to drop 10,000 breadcrumbs per second, aren't I going to have to walk really, really slowly? I'm going to have to be dropping tons of breadcrumbs. But the bad thing is won't the number of breadcrumbs being dropped, because we go so slowly, it's going to cause the graph to form really slowly, right? But it's going to be more accurate. So, I don't know, maybe we say, instead of a t-step of that 0.1 number, what if I did the 0.01? I think McKenna's was originally set there. So if I hit graph now, it's really going slow. It's more accurate than before. Last one was like really kind of zigzaggy and slashy. It's going really slow, but it's a nice smooth curve like it should be. You can see it's like kind of laboring. Okay, put a breadcrumb down, put another one down. It's going really, really slow. You guys get the point? You could also say, you know what, I'm kind of tired of this thing going so slow. Why don't I set my t-step at a much bigger number, like 2 or 100 or something like that. So this would mean like a very long time between breadcrumbs, like 2 seconds, if you will. So this time when I graph it, look what it does. I'm only getting just a couple of data points to connect there. And so it's very, kind of connect the dot-ish and not very accurate. If I wanted to have like a super accurate, I could be like, you know what, I want my t-step to be 0.00001. So that means I'm going to be putting down a breadcrumb very, very frequently, every like 1/100,000th of a second or something like that. So here you hit the graph. Oh, window range, what did I do? Let's see here. I must have put that in the wrong spot. 0 to 30, -8 to 8. I wonder if I made it too tiny. Let's go 0.001, something like that. There we go.
This would take forever.
So you can see now that this is a much better graph than the previous one because I made my t-step go from 2 to 0.001. But you can see it's going to take forever, right? It's going to take a very long time for us to see the complete graph. That might not be a big deal. If you want to go sit down and eat dinner and come back, it'll be complete probably. And it'll be really, really good, but it's going to take a long time. I found that 0.1 is a pretty happy medium between relatively quick and accuracy as well. Does this make sense? Sean, what do you think? Okay. So while this thing is graphing, I'm going to go ahead and stop it. I'm going to put it back to that 0.1. I wanted to ask you guys a question or two about this. And then I have a little sort of a project for you to try. So here it is. So you look at something like this. There it goes. So this graph is like any other graph. You've got y's and x's. The y and x are both in terms of t, as you've seen. Well, what if I were to ask you guys, it wouldn't work very well on this one to ask you about a horizontal tangent line. What if I asked you about a vertical tangent line? How many different places, at least on this part of the graph, have a vertical tangent line?
2.
2 different x values, right? 2 different x values. Yeah, I would agree with you that, well, let's see here. I guess it would be plus or minus 5, right? Makes sense based on our original equation. So over here would have a vertical tangent line. Over here would have a vertical tangent line. But for how many t values do you think we would have a vertical tangent line?
What is T?
T is like a time. So as time starts, x and y are going to do what they're supposed to do based on the pattern that we've given to them. So like that t we had in there, like it was like 5 cosine of t, I think. Say again?
6.
6, yeah. So I'd say this right here, this is a t value. Oh, darn it, you can't see it. Yeah. Sorry. Over there, the lower left, there's a vertical tangent line, isn't there? That would be a t value. And if you just move up, do you see the 2 more up above it? I'm just looking on that. I don't know if that drags screen. It's kind of like corresponding with where my mouse is. There we go. So there. And there. Do you see it? Don't we have the same kind of thing on the right side? So you could have multiple horizontal tangent lines, multiple vertical tangent lines, and it's all okay. You can see them graphically, right? We can find them too. We'll find them analytically as well. Okay, so McKenna said, what is t? What is time? We're going to think it like literally as time goes on. Like as the clock ticks around, then x is going to be something and y is going to be something. And as the clock continues to tick around, x and y are going to be something else. And we'll practice this. We'll actually graph these by hand here in a second. But I thought we'd finish with a little challenge for you guys, and that is right here. I want you guys to start messing around with these, and I thought I would see if you can do this. Using the little ball thing, can you make a ball bouncing up and down in the first quadrant? Literally, just like a basketball. Bounce, bounce, bounce. Up and down it goes, right? Think of a basketball bouncing up and down in the first quadrant. See if you can do it. Feel free to work together. I'll show you an example of how that could work here in just a second. So kind of the typical...
Yeah, that's bad.
Dude, it changed the thesis to actual dribble, like, time. Like, it's like real life.
Yeah.
There's this too, like, spazzy.
Typical would be something like this.
That's what my dribble looks like.
Let's see here. 5
Goes off your foot.
plus 5 cosine of t, something like that. And then you hit graph.
Stop. Hold on.
You get the
There
ball.
we go, I slowed it down.
Oh.
guys.
There you go.
Whoa.
My window's a little bit too short.
500 times.
Goes too high.
Lenny, I slowed it down for you.
That's really slow. See, I set my T max to 1,000.
So it's just going to keep going for a long time.
Yeah.
I like it.
100, 200 times. So my T step is 5.
Maybe because
Okay, so here is the bouncing ball. You've all seen it on yours.
Sit at home all very good.
Okay, so let's try the other one. Make a ball bouncing from the origin to the right with a decreasing height with every bounce. So basically in the first quadrant again. So I wanted to, instead of just bouncing up and down in the same spot like that is, this time I want to see if we can get it to bounce from, like in the first quadrant, basically from the origin out to the right, but be getting like more realistic, right? Because if you toss the ball, it's going to bounce high and then lower and then lower and then lower and then lower and then lower, so on and so forth. So see if you can create that. A little more challenging.
You shift it up.
I think what I can do, I think I can take what I had before and just make a slight modification to it. What I'm going to do is I'm going to change my x1 over to a t. That'll allow the x coordinates to go from 0 to 1 to 2 to 3 to 4 to 5. So it's going to move across the page. Then over here, what I'm going to do is I'm actually going to, I think, take the same equation that I had before for the bouncy ball. But then instead of, well, here, I'll tell you what. Let's look at it like this. If I just did this, maybe this will help you kind of build it up. If I just did this, if I just left it the same as before, but I made my x's equal to t, then look what happens. It just goes bounce, bounce, over and over and over again. But it stays the same height, doesn't it? Here's one thing I can do with my t's. This is not going to be the greatest bouncy ball, because a bouncy ball should probably have a sharp point down there at the turnaround, the bottom turnaround points. We can mess around with that too if you want. But what I'm going to do here is I'm going to take my original height, 5 plus 5 cosine of t, and I'm going to divide it by t. Does that make sense? If I divide it by t, if t goes from 0 to 1 to 2 to 3 to 4 to 5, dot, 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 every time t moves up, isn't the thing that I divide by going to move up as well? Therefore, making the entire value of the height lower. So if I do this on a graph now, there's the first height, second height, so on and so forth. This is actually pretty dramatic, isn't it? It's pretty quick decrease in height, but you can see the height is decreasing towards 0, as was mentioned. If you wanted to make it truly a sharp bounce, and Sean, I can't remember if you did this. Did you use absolute values?
Yes.
The absolute values will make it a sharp bounce. So you could come down here and do absolute values of, I guess you could just go 5 cosine t at that point. And then divided by t. See what that looks like. So there's kind of your sharper bounce. Something like that. Maybe a little more realistic on what a bounce would really look like. So, okay, so I just wanted you to kind of fool around with this and get a sense of how, if you mess around with x, if you mess around with y, what it's doing. But let's go back to what this is. Isn't this the particle moving back and forth along the x-axis? But now we're freeing it to move up and down at the same time. Left and right and up and down. Okay, so let's take a look at maybe one example here. I know we're up against the last 10 minutes or so. And here we go. A parametric equation is an equation in which both x and y are depending on time, is what goes in the blank there, as we talked about earlier. Occasionally, often, I don't know what the right word is there, the graph of a parametric function is going to fail that vertical line test. That is because y and x are functions of time, or t, not necessarily y being a function of x. You can do it that way. You can create a function of y in terms of x with parametrics, but it's not restricted to that. So for these examples that are coming up here, we're going to just basically be plotting some points. And so let's at least do one of these, and I might show you a little bit of calculus with this as well here today. So take a look at this first example. Let's see here. Can I fit this? There we go. Okay, so guys, you've gone all the way through calculus. We're going to just plot some points. Really simple stuff here. So if you would do this with me, if t is -1, x is
-3.
very good, and if x is if t is -2, x is
-5.
just roll on down. What about the 0?
-1.
What about the 1?
1.
And then the 2, you get
3.
very good. Okay, so with the y, if you plug in a -1, you get 2. Then
3.
plug in a 0 and you get,
1.
plug in a 1 and you get,
0.
and finally plug in a 2 and you get.
Negative.
So all we've done here, as we said, is t progresses from here to here to here to here to here, whatever. I realize I did flip around the -1 and the -2. But as you progress in your t's, your x's and y's are going to do whatever they're going to do based on the rule of those two functions. So what we could do now is plot these points and see what we get. So -3, 2 is right there. -5, 3 is there. -1, 1 is there. 1, 0 is there. 3, -1 is there. Oh my goodness, what is this?
It's a line.
It's a straight line. And so what we typically will do is we'll connect these dots and we'll put in an arrow or two indicating the direction of motion. So I'm putting those arrows in there, indicating that it's kind of going from upper left to lower right. And then the last couple things I want to think about here, eliminate the parameter by substitution. This is, I'd say, a very rare occurrence, but it could happen. What we can do here is we can take the x equals 2t minus 1 and the y equals 1 minus t, and we can basically eliminate the t, eliminate the parameter by using substitution. So an example of this would maybe be to come over here and solve this for t. So it would be 1 minus y equals t. And then I can substitute that into the other one. So it would be x equals 2 times 1 minus y minus 1. I get x is equal to 2 minus 2y minus 1. And let's see here. It's going to be x minus 1 equals -2y. Apologize for doing this fast, but I'm assuming you guys are all pretty solid on manipulating linear equations. Okay, so I finally end up with this. Does that look like the line we just graphed? Does the line we just graphed have a slope of -1/2? Yeah, down 1, right 2, down 1, right 2. What about the y-intercept of the line we just graphed? Does 1/2 seem pretty reasonable?
Yeah.
I think so. So please don't look at that and say, cool, I'll just always eliminate the parameter. There are going to be times when it's either going to be impossible or highly inconvenient. I'm serious. I mean, you can believe me or not. It's up to you. I hope that you will believe me. It's going to be a whole lot easier, I think, in almost every case for you just to work with the parametric. I just want to show you the connection between the new stuff we're doing right now and the old stuff we've done in the past. So you can write most anything in terms of parametric, anything we've done in the past, as well as kind of newer stuff too. So let's see here. Let me decide what I want to do. We'll do another series of those tomorrow, but I thought I would do this.
Oh boy.
This will be good. This will be good timing. Okay. We'll come back. We'll do more development with the parametric stuff, like what the graphs look like. But I thought what we could do is finish with this. And let me do that so you can see a little bit better. How do we deal with calculus and parametrics? So in calculus, we obviously are interested in derivatives and equations of tangent lines and things like that. And so let's just talk for just a brief second here about how you find the slope of the tangent line for a parametric curve. You're going to find out it's not that bad. I know it looks scary, I get that, but it's not that bad. So if you've got two different parametric components here, x equals something and y equals something, then the slope of the curve, right? So the slope of the tangent line at the point x, y, whatever that is given by this right here. I'll write it over here just to clarify. dy dx is equal to dy dt over dx dt. So in other words, you take the derivative of whatever that is, and you take the derivative of whatever that is, and you divide them in the pattern we see up there. You do the dy dt over the dx dt. Of course, dx dt can't be 0 for this to exist, right, because it's a denominator. How does this work? Any thoughts on how this works? Like, why is this true?
Would you just, I think that's like a fraction. Like,
There's some deeper reasonings, but I would like for you to think about it like that right now.
okay, like
What do you do with-
copy dot plot,
Yes.
and it comes up.
Can't you say dy dt times dt dx? Like literally, if you copy dot flop it, and you get this. Like I said, there are deeper reasonings for that, but for now, this is a great way to remember it. dy dt over dx dt, you copy dot flop it, the dt's cancel out, and you get dy dx. And we'll do something similar with that when we get to that second derivative tomorrow, probably. But I want to at least show you that right now. We'll go back to parametrics tomorrow, and we'll do some more practicing with calculus with parametrics tomorrow as well. So, you good? That's more playing with your calculator you've done in a while, right? I hope.
It's very true.
Hope that was fun. Hope you guys have a great rest of your day, and I'll see you tomorrow.